Actually discuss the Sturm-Liouville boundary value problems, and the Sturm-Liouville problem is the differential equation derivative of pxy dash plus lambda qx plus rx y is equals to 0, where we are differentiating the p function. That means p function should be differentiable, and q and r are any two continuous functions over the closed interval a to b. And whenever such an equation is given, we say that such equation has eigenvector depending on whether there is a non-zero solution y corresponding to some real number lambda, right? If this differential equation has some non-zero solution yx over the closed interval a to b for some particular fixed value of lambda, then that non-zero solution is called eigen function corresponding to that particular value of lambda. So that is the concept of eigen function, and we have taken the special case that legendary equation is a example of Sturm-Liouville problem, where we have the px function to be 1 minus x square, right? That is coefficient of y dash, and there is only this term times y we have. So that means the coefficient of y is a number, and therefore we are taking when we get the legendary equation as a special case, we can take rx is 0, qx is 1, and lambda is that number pp plus 1, right? So in that case, the legendary equation is example of Sturm-Liouville problem, and then we have seen that for different values of lambda depending on natural number, we have different non-zero solution, which are the Legendre polynomial, and Legendre polynomials are orthogonal if m and n are different. So that concept we have extended here, that if we have two eigenfunctions corresponding to two eigenvalues, then using the same steps which we use to prove the orthogonality of Legendre polynomial, we will get the orthogonality of the eigenfunction ym and yn depending on whether this term is 0 or not, right? So for orthogonality, we need this term to be 0, and this term depends on this Wronskian value of the Wronskian at the end point of the interval, closed interval AB, right? So if WB and WA is 0, or PA and PB is 0, then we get this term to be 0, and this, whenever this term is 0, we will get orthogonality of ym and yn, right? So whenever we consider the Legendre equation, PA and PB is 0 because the polynomial is 1 minus x square, right? And that is, we also mentioned here that in the Legendre equation, the px term, if we compare with the Sturm-Liouville problem, then px term is 1 minus x square, which is 0 on the interval at the end point of the interval, right? At minus 1 also this is 0, 1 also it is 0. So PA is also 0, PB is also 0, and therefore we get the orthogonality of the Legendre polynomial using this general computation. And on the other hand, if WA and WB is 0, in that case also we get the orthogonality. So that we discuss here, that whenever we take this boundary condition, WA and WB is 0, and therefore we get the orthogonality of ym and yn, right? Similarly, whenever take the other boundary condition in terms of the first derivative, WA and WB is 0, that means we get the orthogonality in that case also. Yeah. So now that is regarding the orthogonality of the eigenfunctions, but the first question is how to find the eigenfunction, and that is the we will discuss in the examples. So whenever eigenfunction exists and we take the corresponding boundary condition, the eigenfunctions are orthogonal. Only thing we need to understand is how to find the eigenfunction. So the simplest second order Sturm Liouville equation is of one of the example is of this form: y double dash plus lambda y is 0, and we are taking this condition, which is this second type of condition, right? So we are basically taking this boundary condition y dash at end points to be 0. So y dash at end points. So here the end points we are considering the interval 0 to pi. Just a minute. So the statement is the boundary condition is in terms of 0 to 0 and pi. That means we are considering the interval closed interval 0 to pi, and we want to find all the possible value of lambda for which the corresponding solution y is non-zero. They are the eigenfunctions. So we are starting with the first case. One by one we'll take the value of lambda, and depending on what is lambda, we'll find the characteristic polynomial, because this is the second order linear differential equation with the constant coefficients, right? So depending on what is lambda, we'll get the corresponding characteristic polynomial, we'll solve it, we'll find general solution, and then we'll find the general solution. Among that, what are the solutions satisfying this condition, right? So first case we have considered is lambda is 0. In that case we get this differential equation, and that will give us general solution using the boundary condition y dash 0 is 0 or y dash pi is 0. We will get beta is 0. That means among the general solution only these functions are there which satisfies the boundary condition, but we need eigenfunctions which should be non-zero. So that means we are taking particular value of alpha to be 1. We can take alpha to be 2 also. So all those are the eigenfunctions corresponding to lambda is 0. Okay, so general answer is, what are the eigenfunctions corresponding to lambda is 0? The answer is yx equals to alpha when alpha is non-zero. Right, so this is the general answer. The second case is that so we have considered the first case lambda is 0. Now we are taking lambda is less than 0. So we are solving this equation when lambda is less than 0. So if lambda is less than 0, that means we can write it in this form where m is some real number. So subtracting lambda is equals to minus mu square, we get this characteristic polynomial. And it has two roots m1 and m2 which are different because m is non-zero. We get this general solution, right? And then among the general solution we need to find the solutions which satisfies the boundary condition. So for boundary condition we need to find first derivative, and then we evaluate it at 0 and pi and equate it to 0, right? So if we take y dash 0 equals to 0 boundary condition, if we using this equation, then we get c1 is equals to c2. So all the solutions yx satisfying this boundary condition must have c1 is equals to c2, right? And all the solution which satisfies this first condition along with the second condition That means C1 is equals to C2. We have substituted here. C1 is equals to C2. So essentially we get C2 to be 0. Right. So using these two boundary conditions, we are getting C1 and C2 is 0. That means all choices of y will be 0, right? Because C1 and C2 is 0. So we get only single solution, which is yx equal to 0. And we know that eigenvector cannot be 0. Eigenfunction must be non-zero function. So that means there is no eigenfunction corresponding to lambda is less than 0. That means lambda is less than 0 is not an eigenvalue. Right, because there is no eigenvector corresponding to that. So let us write down that lambda is equals to 0 is not an eigenvalue. Okay, now third case, which is lambda should be positive in this case. So if we have this differential equation and if lambda is greater than 0, then now we are checking whether lambda greater than 0. That means lambda is equals to 1, lambda is equals to pi, lambda is equals to root 2. All these are the real numbers for which whether this differential equation has a eigenfunction or not corresponding to that value of lambda. So since lambda is greater than 0, we can find its square root, right? So suppose, yeah. So since lambda is greater than 0, therefore lambda is equals to mu square for some positive, for some real number mu. Right. So it is square of some number because it is positive. Now we substitute this in the differential equation. So differential equation is y double dash plus lambda y is equals to 0, and we substitute lambda is mu square. We get this differential equation, right? So therefore, the corresponding characteristic equation is so what will be the characteristic equation corresponding to this equation? It will be m square plus mu square, right? M square plus mu square is equals to 0. So what will be the roots?
Plus minus
Is a
I.
real number. Correct. So that is m is equals to plus or minus mu times I, right? Because mu is a real number. Correct. So now we have these two different values of m1 and m2, and m1 and m2 are complex numbers. So this is the third case of the second order linear differential equation with a constant coefficient. So that means what will be the general solution? So what we do, we compare it with yeah, alpha plus or minus beta I, right? So that will give us alpha is 0 and beta is mu. And then we know that whenever we have value of m to be this, the solution is e power alpha x times c1 cos beta x plus c2 sin beta x, right? So just substituting alpha is 0 in that, we get c1 cos mu x. So beta is mu here and c2 sin mu x, right? So this is coming from the third case of second order linear differential equation when we have two complex roots which are distinct, right? So now what is the next thing? We will use the boundary conditions. So for boundary condition, we need to first find the derivative of these. Derivative, we know that the derivative of cosine function is minus sine function, and the derivative of mu x is the mu will come out, and plus c2 times derivative of sine x is cos x function. So this will be our derivative, and now we shall use the boundary conditions. So using first boundary condition, which is y dash is equals to y dash of 0 is equals to 0. So what shall we get here? If we differentiate and substitute 0, we get 0 equals to y dash 0 is equals to yeah, so we know sine 0 is 0, right? And cos 0 is 1. So that means
mu into C2.
we shall get
Mu into C2.
mu into C2, right? So if we use this equation, we are getting mu into C2, and then we know that mu is non-zero, right? So since mu is non-zero, what shall we get? C2 is equals to 0, right? Why mu is non-zero? Because we have taken lambda is equals to mu square, and lambda is positive. So that means mu is also non-zero number. Fine. So now if we substitute C2 is 0 in the given general solution, that means this term will cancel out, right? Because C2 is 0. So if among all the solutions satisfying first boundary condition are of this form, right? Because C2 is 0. So now among these, we shall use the second boundary condition. Second boundary condition is y dash phi is 0. So we get 0 is equals to, now we substitute x equals to pi in this equation. So we get minus c1 mu sine mu pi, right? So because this part is 0, C2 is 0, correct? So only in the y dash term also now we have only this function. So now if this is 0, what are the possibility? We know mu is non-zero function. Can we take C1 to be 0? So we are looking for the non-zero solution by. We are looking for the non-zero solution by x, which is equals to C1 cos mu x. And we got this equation. So this equation will imply mu is non-zero. That means either C1 is 0 or sine mu pi is 0. So can C1 be 0? If you take C1 be 0, then our yx function will be 0 function, right? And if it is 0, then it is not Eigen function. So that means, so if you want, we can write down this. Yeah. So therefore we get C1 is equal to 0 or sine mu pi is 0, right? So if we take C1 to be 0, then our yx function, which is basically C1 cos mu x, will be 0, right? And if y is 0, then in this case there does not exist any eigenfunction, right? Because the general solution satisfying this two equation boundary condition when c1 is 0 function. So on the other hand, so what are the solution of sine mu pi is 0? We know the roots of sine function, right? So if sine mu pi is 0,
Mu
that
is
means mu
mu
pi
is
is
integer.
right. So integer times pi. So what you said is correct. That is the mu is mu is, mu is an integer. Right. So now what did we go? We got in this case. Let us summarize that. So we started with lambda is positive case. So if lambda is positive, what are the non-zero solutions of this equation? Depending on the boundary condition. So we got this general solution. Among the general solution, non-zero solution we are getting only when mu is a integer, right? So if mu is an integer, that means basically mu is equals to n we are getting here. So let us substitute this in the equation. So therefore the non-zero solutions y is equals to c1 cos mu x, and mu is n, so that means we are getting cos nx, right? And corresponding to lambda is equals to, so what is lambda? Lambda is equals to mu square in this case, right? We started with case 3, which we have taken lambda is positive, and we assume lambda is mu square for some mu, and this mu turns out to be n, so that means lambda is n square, right? So that means the non-zero solutions are eigenfunctions corresponding to eigenvalue lambda is equals to n square. So since lambda depends on n, it is in terms of n, we write here lambda n. Similarly, this also depends on n, we are writing here yn. Right. So just summarizing that, therefore ynx is equals to c1 cosine nx are the eigenfunctions corresponding to eigenvalues lambda n is equals to n square, right? So here we are not getting any condition over c1, am I right? So in particular, if we want, we can we can take special function, like we can assume c1 is equals to 1, right? So we can write that here we are taking c1 to be 1. So we can take c1 to be 2 also, because c1 is any arbitrary number. In that case, the corresponding eigenfunctions will be 2 times cosine nx, right? So in this example, what are the possible eigenvalues? Either lambda is 0, right? Only eigenvalues are lambda is 0 or lambda is equals to n square. So any real number which is other than 0 and square of a natural number is not an eigenvalue. That is what we shown here, and all these numbers we have found the corresponding eigen functions. Okay, so I think this is regarding this particular topic which we started in the previous lecture. So now we want to discuss a related concept, that is Fourier series. So now onwards, we will be discussing only applications of this course. Basically, we will be discussing Fourier series, Fourier integral, and Laplace transform. And this topic has several applications in solving differential equation, partial differential equation, and it has application in studying signals, input output, and particularly Laplace transform has many applications in engineering. So this is, we studied the expansion of function in terms of legendary polynomials using the orthogonality of the legendary polynomials. The same way, this topic is related to that. So we know that what are the odd functions and even functions, and we know that if given function is odd, then there are simple properties of integral that if we integrate over the interval minus L to L, then we get the value to be 0, right? So example is sin x function. Similarly, if f is an even function, then the integral will be twice the function, twice the integral over the half interval. So what is L? L is some number, right? So further we will use certain other formulas which you already know in special cases. So first formula is, all these formula we will need to find the Fourier series of particular function. So first, if we integrate my sin n pi function over the interval minus L to L, the value of the integral is 0. Similarly, if we integrate cosine function, then also the integral value is 0. Right. So this is simple to show. In if you you already know these results when L is equals to pi. Right. So in that case, integral is minus pi to pi sine nx dx, and that value is 0. Just we need to integrate. Okay. So next formula is, if we integrate minus L to L sine m pi x divided by L cos n pi x divided by L dx, then this turns out to be, yeah, so what will be this value? This will be essentially half integral minus L to L. We can use so basically we are using trigonometric formula. So if we have true SC, then it is S plus S, that is sine plus sine. And then we know if we substitute the limits, if we integrate and use this integral of sine, essentially we get both the integral to be 0. Right, so this integral is always 0. Same way, if we have integral minus L to L sine m pi x divided by L sine n pi x by L, so that will be half cosine m minus n pi x by L minus cosine of addition and then again using the first formula for cosine function, this turns out to be depending on the what is the value of m and n. So if m and n are different, you can verify that this value is 0, and if that is same, then the value is L, because if it is same, this part will be cosine of 0, right? So in that case, you will get the value L. Okay, and similarly, so this is sine into sine integral formula. We can also do cosine into cosine formula. That will be the last formula, minus L to L cosine m by x divided by L cosine n by x by L dx. So what is L? L is some positive number. So this also you can verify that this is 0 if m is different from n, and it is L if m is equals to n. So what is the one of the formula here is this formula, which is inner product of sin x function with cosine x function is 0. Right, so the way we have the formula that the Legendre polynomials are orthogonal, that means integral of Pn and Pm is 0. The same way we have observed here that the inner product of sin mx with sin nx, right, m and n are different, then this inner product turns out to be 0. So that is basically the orthogonality of cosine and sine function, and we usually get cosine and sine function as a eigen functions. So see the previous example, we got the eigen functions which are cosine functions, right? And the Legendre polynomials are also eigen functions which are orthogonal. Sine cosine functions are also we are getting as an eigen functions depending on the third case of differential equation, second order linear with the constant coefficient. So we get the solution in terms of cosine beta x, sine beta x. So we get the orthogonality of sine mx and sine nx function, and whenever we have orthogonal functions, we can expand functions in terms of series. So which function essentially we are looking for here is the periodic functions. So we know that a function fx is said to be periodic if we have fx equals to f x plus 2 times L for some positive number L. Right. So in this case, this number which is coming as a difference between x and x plus 2L is essentially the period. Period is 2 times L. So example also we know sin x and cosine x functions. So what is the period of sin x function? Sin x plus 2 pi is sin x, right? So that means this number which is 2L, and that will give us L is equals to pi. Right. So period is 2 pi, and that gives us L is pi. So whenever we have such a periodic function with given period, we can find it Fourier series expansion. Yeah. So let us write down the definition of the expansion. So of course, for every function we cannot do this. If you remember, we have assumed continuity or at least integrability of the function when we discuss Legendre series. So each integrable periodic function fx we can represent as a Fourier series. So how do we represent? So basically we are writing fx is equals to a0 by 2 plus summation n1 to infinity an cos n pi x divided by L. So here we are assuming the period is 2L. Right? Period is 2L. So that means we are dividing it by L, and the second term is summation n is equals to 1 to infinity bn sine n pi x divided by L. So if you remember what we how did we derive this coefficient an in the Legendre expansion? So we have taken the inner product with cosine and sine functions, and we use orthogonality. So if we use that similarly, then we get the constants a0, which turns out to be 1 divided by L minus L to L fx dx, and the other coefficients for natural number n are 1 divided by L minus integral L to L fx cosine n pi x by L dx. So these terms involve cosine functions. The other terms involves sine functions. So the an term, which is coefficient of cosine terms, which involve cosine term in the integral. The same way, the coefficient of bn, which is a sine function, so that bn involves sine function. Right. So this is essentially the definition of Fourier series. The Fourier series of the function fx is this right hand side series where the coefficient of a0, an and bn we are going to find using these three integrals, and we have written it to be equal, but this both terms fx and this series are equal only when the function is continuous at that point. If it is not continuous, then it will not be equal. So let us write it in this form, right? So it is equal only when the function is continuous at that particular point. Otherwise, fx will not be value of this series at that particular point x. Right. So let us first take some examples on how to apply this formula. And before that, there is one remark that for L is equals to pi, we get the Fourier series turns out to be the series is an cosine. L is pi. So L is pi means in this term, if we substitute L is equals to pi, we get cosine nx. Right. Similarly, here we get sine nx by substituting L is equals to pi. So this will be cosine nx plus summation bn sin nx when our period is 2 pi. Right. For the sine, similar to the sin x and cosine x function, the period is 2 pi. So if our function has period 2 pi, we shall use this formula where in the a0 formula also we substitute L is equals to pi an is equals to 1 by pi minus pi to pi fx cosine nx dx, and bn is also defined similarly. So now the interval is, instead of minus L to L, it has become integral minus pi to pi fx sin nx dx. So whenever in the example the interval is given, so depending on the period of the given function, we will find this corresponding formula, and then we'll substitute what is the fx function in that interval, and find out what is the Fourier series. So this is first remark. Second remark is regarding the two cases, whether the function is an odd function or even function. So if f is an odd function, then what shall happen? So you can see here that if f is a odd function, then among ans and bn, which term will be 0? We know that cosine function is even function and sine function is odd function, right? So if f is odd, then which of this integral will be 0? So if f is odd, then odd into even is a odd function, right? So that means this will be an odd function, right?
Yes, sir.
And that means an is 0. Similarly, a0 also will be 0. So that is just a remark that whenever f is an odd function, then in its Fourier series expansion, there will be only Bn terms. So essentially we get summation 1 to infinity Bn sin nx, where Bn is defined in this way. Right, so we get this part. And similarly, if f is an even function, so we get right here, but then a0 and ans are 0, hence we get this expansion. Similarly, if f is an even function, then instead of being an is 0, you can observe that each bn is 0, and we get the expansion of even function as a0 by 2 an cosine nx, where an is given to be 1 divided by pi minus pi to pi fx cosine nx dx. Yes, so this is regarding the whenever the function is odd function, we get the basically we get the sine series, right? And whenever we have the even function, we get the cosine series, right? Because the first term we can get from this term if we take n is 0. So essentially we get the a0 term.
So,
Yes.
so when f is an odd function via a0 and an0,
So f is an odd function. We have observed that the property of odd function, that whenever we have an odd function, then such integrals will be 0. So over the symmetric interval. So if we see here in this case, so in this power series, whenever f is odd function, we know that cosine is even function. So odd into even is odd function as a multiplication of these two functions. And whenever we have odd function and we integrate from minus L to L, we get the value of the integral to be 0. Right, and here we have only fx function which is odd function, so that its integral turns out to be 0 function.
okay, sir.
Right, so this is following directly from the properties of integration of odd function and even function. So the last thing what I want to mention is that if the function is odd function, we are getting sine series. If the function is even function, we are getting cosine series. But in general also, if the function is not odd, neither odd not even function, in that case also we get the Fourier series in these two parts. The first part is cosine series, the second part is sine series, right? So whenever we are given some function and it is asked that find cosine Fourier series, then we'll find this part. And whenever we are asked that find the sine series, sine Fourier series, then we need to find this Bn part.
So in cosine Fourier series, only that after that summation is the part of that, right?
Yeah, but A0, if you observe, compare these two, why we are calling it A0? Because essentially the formula is same, only we are substituting here n is 0.
Okay, sir. So A0 is also included in the cosine Fourier series.
Yeah, so that we can combine, consider as a part of cosine series. Okay, so I think this should be enough for today.